Swayam Prabha. Digital India. Educated India.
So this is one way of doing it, divide and conquer, great, it's good application of divide and conquer to geometric algorithms, but we will do something which actually will be even simpler in terms of, it will be conceptually much simpler, okay. So, and that idea is the following. What we do is, another method to compute. So what you do is, you add, so we are given these points P, right, given P, we add the points in some order and maintain, let me not write one, maintain the closest among the points added. Okay. What do I mean? Well, okay, I have all these points, okay, given to me. So this was the given set of points. I add them in some order, okay. So maybe I add this point and this point and this point. So this is some arbitrary ordering I am choosing right now. These are 9 points. So initially, of course, I don't have any points. So I first start with these first 2 points, right, and the first 2 points define some kind of a distance between them. So among these 2 points, of course, this is the closest pair, there is no other point. The next point I add is 3. Okay. So when I add 3, I basically want to check. So I want to now, after adding the third point, I want to again have the closest pair among the first 3 points. Now it could be that the closest pair remains, remains unchanged, or the closest pair changes, right. There are these 2 possibilities. Right. So let me use another notation. Let me say that Pj is the subset of the first j points, okay, and let us say delta j equal to the closest pair distance within this subset of points Pj, and the closest pair themselves itself could be denoted by, and okay, so just let it be less. So I think this should suffice. So I am maintaining basically the closest pair distance of the first set of j objects, and this varies from j equal to 2. So for j greater than or equal to 2 to j less than or equal to n. So I start with 2 points and I end when all points have been added, and if I am correctly maintaining the closest pair distance, I get it. Okay, it's absolutely trivial, right? I mean, there is nothing algorithmic that I have done here. Okay. And if you just implement it like this, okay, a naive implementation would require this kind of computation. Okay. So, a naive analysis would be that when we add the point Pj plus 1 to Pj such that Pj plus 1 is nothing but Pj union the latest point that you have added. So, when we do this, we can check all the distances dist Pj plus 1 with Q, where Q basically belongs to Pj. So, when the next point comes in, I basically see, check the distances with respect to all the points and compare with delta G. So, whatever was the closest pair distance till now, the new point comes in and we look at all the pairwise distances and we check if delta J is if let me put it like this, if necessary, so if any of these distances basically is smaller than delta J, if any of the newly computed distances is smaller then update delta G. Now, if you do this, what is the kind of time complexity? Is it clear that this will a very simple algorithm will work? So, time complexity will be what? In the jth step, what are we doing? We are computing j minus 1 distances, or the j plus first point is the j plus 1 distance. So, the running time is going to be summation of order j equal to, let us say I did it from 2, does not matter, I can write maybe j is equal to 3, because I am adding from the third point all the way to n point, and this is order n square, right. Again it is that 3 plus 4 plus 5 plus 6 all the way to n, and that is about order n square. So, we have back to square one, right. We started with a naive algorithm where we said we compare every pairwise distance, and we wanted to do something better than that. And I just said that I motivated by saying that this kind of a method, well, we had a divide and conquer algorithm, but this one was supposed to be at least as good as that and actually simpler. Okay. But it is simpler, no doubt, right. You agree that it is much simpler than a divide and conquer algorithm. Okay. I am not doing anything merging this thing, nothing, no divide, no merge, nothing. I am just naively sort of updating the closest pair distances inductively and finally outputting the answer, but then we are stuck with this running time of n square. What do we do? Okay. So, I will give a slight twist to this algorithm, okay, and the slight twist is twist to the previous. So, this kind of approach is called incremental algorithm, right, because I am incrementally adding those points. So, I can do this not only for this algorithm, and as we will see, the generalization of this algorithm is that suppose I were to construct a convex hull, I could always add these points in some order and maintain the convex hull, finally get the convex hull. I want to construct a Voronoi diagram, I could add those points one after the other and maintain the Voronoi diagram, big deal, right? Finally, I get the Voronoi diagram. So, this is an incremental algorithm, and the twist that I am mentioning is that we will add, the only thing that is left somewhat undefined is we will add the points in a random order. So, I just said we are going to add the points, I did not say how we are going to add the points. Now, I am saying I am going to add the points in a random order. Now, the random order means that all permutations are equally likely. Okay. Random order in this context is a random permutation. So, these points are given as P1, P2, P3, Pn. So, I am going to add the points in a random order, okay, where each permutation is equally likely. Each permutation. Okay. Just to emphasize this point, you know, one possible way is we can start the algorithm by generating random permutation and add the points in the same order. Okay. So, I could say that this permutation is basically P1, P2, P3, Pn, okay, and follow this order for insertion. We could do that, okay. Or we could also think about it like among the remaining points in phase or stage J, so we have this piece of J, right, the first J points are added, we pick a point uniformly at random from so the initial set of points is P minus Pj. So, we will just pick one of the points that we have not added uniformly at random and use that sequence. So, these are equivalent things, either I can generate the random permutation initially or I can follow this. Both will basically give me the same outcome. Okay. And this is the magic. I mean, it looks, you know, we seem to be relying too much on our luck. Okay. What can a random permutation buy us? Okay. But I am claiming that, you know, this is basically the magic. And when we do the analysis, we will exploit this fact it's a random permutation. However, there is a catch. Okay. The catch is that this algorithm is no longer what we called a deterministic algorithm. So, I believe that you have seen some examples of randomized algorithms in this school, in this series of lectures. So, here is basically again looking at the same thing, probably in more details. Okay. So, since I am using a random permutation or I am picking the next object at random, okay, so this results in a framework or randomized algorithm okay, and the framework is called randomized incremental algorithm, or I will actually use the acronym RIC. Have you been introduced to this term RIC before? Yes. Okay. So, this is, I am just getting down to probably more basics. So, this is how basically we define the framework of our randomized incremental construction. It is a very simple framework where you basically add the objects one after the other and inductively maintain some property, in this case the closest pair distance, and you update it. And the way of adding the next object basically is a randomized strategy. Now, once we say something is a randomized algorithm, okay, what do we really mean by randomized algorithm? Okay? I just want to be a little pedantic here, and I want to emphasize a couple of things. So, one is that there is no assumption. No, so the exact implementation we will discuss. Okay. Right now I am saying that I am going to pick the next point and find out whether the next point will change the closest pair distance.
With the existing
yeah, whatever with the points that have been added so far. I have not changed anything. So, it is again the previous algorithm, right? It is this thing, the whole thing is this. I am adding the points, but now this 1, 2, 3, 4 is a random order basically. It is not an arbitrary order, but it is a random order. There is a difference. Arbitrary order means, whatever order you give, it is okay. But I am insisting that it is not whatever order you give me. I am going to use the random number generator to generate that permutation.
Is it not an arbitrary order?
No. So, we will see. So, there are some properties of random. See, I am saying that it is a random permutation where each permutation is equally likely. When you say arbitrary, it does not have this notion, right? Arbitrary can be some fixed ordering of these numbers. Arbitrary and random are two different things. Okay? Arbitrary means whatever be the ordering, it is going to work. Random ordering means I have a way of generating a random permutation where I am insisting that all permutations are equally likely. And let me just complete this and we will see what the difference is. It is a very subtle difference. Okay? So, there is no assumption on the input set of points, okay, in which case basically I am saying it basically is worst case. So, you give me whatever points you want to give me and this algorithm will work in a certain way. So, I am not saying that you will give me some random points. So, it is not, the input points are not random, that is what I want to emphasize. Okay. So, input points are not chosen randomly. Very important point. So, it is worst case with respect to input, but the performance of the algorithm will depend on what is the permutation that has been generated. Let me just write this. The running time would depend on the order of insertion. Okay. How is it so? Well, I mean, to give you a simple example, maybe I can just use a linear ordering. So, suppose the points are of this nature. You see the point what I am making, and suppose I am inserting the points in this order, so on and so forth. So, what is happening? So, as I keep inserting the points, every time the closest pair distance is going to change. right? As opposed to if I, this is the same set of points, okay, but I change the insertion order because it's a random ordering. Maybe I insert this and then insert this, then insert this, then sometimes it will change, sometimes it will not change, right? If I insert this, say, first time when I enter the third point, it's not going to change, right? So the ordering is important, could be important in terms of how many times things are going to change, because as things change, we will be forced to do more and more updates to the data structure. So I have not talked even about what is the data structure. There is some hidden data structure that we need to maintain to be able to compute that closest pair when the new point comes in. I am not going to compute the closest pair in a brute force way, the way I have mentioned it. I will be using some data structures. But the important thing is that how often or how much change that the data structure will incur will depend on the order of insertions. Okay. So if I insert it in the ordering I first mentioned, 1, 2, 3, 4, 5, it's in some sense it's a worst case ordering. Okay. But if I choose a random ordering, I could hit that ordering. What is the chance of hitting that ordering? 1 by n factorial, right? 1 by n factorial. So with that kind of probability, I will be incurring this case. Otherwise, it's not going to be that bad. Okay? This is very similar to, if you recall, basically discussions on quicksort. So now I'm drawing your attention to something that you're probably more familiar with.
Sir,
Yeah.
if ordering is in opposite way.
Okay, so order.
No.
Uh-huh.
If 1 and 2 are more close than
Right. Right. That's a very good case then.
Yeah, that is a good case. But using the randomized algorithm, we are disturbing that case.
Okay, so again, whenever, point taken. Whenever, see, this ordering is not known to us, right? It's given a set of points. Whenever we are doing analysis of algorithms, we are always going to look at the worst case performance, right? Never, in fact, I actually tell my students never use the word best case. There is nothing like a best case in the case of algorithms, okay? We are always looking to design to minimize the worst case, okay? So forget about, my ordering could disturb the best possible scenario. There is nothing like it, because that is not known to me. I am basically using an ordering to defeat the worst case. I am not trying to do anything about the best case, okay? We never worry about the best case. The whole metric of algorithm design is to minimize the worst case.
So are we creating another worst case in that using this
We will do that calculation. We will do some calculation. What I am saying is that most important thing is that the running time, let me put it this way. If I go back to the previous page, okay, so let me just say, so the running time, so observation is running time T's of n will depend on the permutation. Okay. So I will write it as, if I fix the permutation, let us say some sigma of n is some fixed quantity if sigma is fixed, right? If I fix the ordering, then the number of changes or whatever is going to be also fixed. If I fix the ordering.
sigma is the ordering?
Sigma is the ordering, yeah. Sigma is one of the permutations basically. Sigma belongs to, let us say, pi's of n, all permutations. So then what am I saying? I am basically saying that if the ordering is fixed, my running time is also fixed, because I know exactly how many updates will be required. And what we are going to analyze is basically the average of this running time, because I am picking one of them at random, right? So we want to analyze the quantity sigma of because one of those permutations will occur with equal probability. And this is called what? Nothing but the expected running time. This is the expected it's just the weighted average, right? Each permutation has 1 over n factorial probability, then there is some running time corresponding to that, I am taking the average. Now, when we do this kind of analysis, okay, which is basically the, it's also known as the worst case analysis of a randomized algorithm. Why worst case? Because worst case with respect to any input. So, I will not make any assumption of the input. Permutation is in no one's control, neither I nor the adversary. We are just assuming there is a fair random number generator, unbiased random number generator. That's only the assumption. And then there is no question of now best case, worst case, right? We are going to hit an average. So, as long as this quantity is small, we should be happy. Not only it's small, this is average, you can do even better analysis by saying we will look at the actually the distribution, and you can look at the tails of the distribution, all that analysis can be done. Right now we are only looking in, I'll be only looking at the expected value. But you can do, you can actually figure out, do with more analysis, how likely or unlikely that you're going to deviate from the expected value, from the average value. That's standard, statistical tools. So, let me just contrast. So, I have written on this half to contrast it with the quicksort. This is something that you are more familiar with. So, recall quicksort. So, quicksort can be thought of also as, I have these points to be sorted. Of course, I don't know the ordering. What I do is I first find a pivot. Okay, this is all points. So this is, let us say, this is the less than, and this is the greater than, and recursively again I do, split this set, and I keep going. Right? I partition, I pick pivot. Now, there are two ways of looking at quicksort. One is that the pivots that I am going to choose is a fixed element. Fixed element meaning that, I choose the first element and use that to split the set. And in that case, you hear these notions, oh, quicksort can then get into trouble because I can do this increasing order, decreasing order, and then the analysis basically says that if your sets are very skewed, that is, let me use this one. So, this is a bad partition for the quicksort. So, if I partition like this, only leaving out only one element, next time also leaving out one element, every time I do this, I am actually paying the price for partitioning, which is about order n, and I am only able to basically shrink the set by one element, right. That is basically, that leads to that order n square behavior. And you are saying that, if I pick the first element, then, and if I know that, you're going to pick the first element, I'm going to actually give you an ordering that will make the algorithm execute the worst case. That's the whole point, that, we cannot assume that the input will be given to us in a way where it will be some, you can always think about it as an adversary. The input is coming from an adversary, it's an adversarial input. So, the moment the adversary knows my algorithm, the adversary will always try to basically make my algorithm run as slowly as possible. Okay. So, if the adversary knows that I am going to pick the first element to do my partitioning, then the adversary can, the worst case analysis will obviously be an increasing or a decreasing kind of a sequence. Right. But on the other hand, if I pick this pivot at random, then you are not going to encounter such a case easily. Right. Only in the case that the pivot that you pick happens to be the first or the second, that first element, and that probability is 1 over n, right. That probability is only 1 over n. So, you should think about quicksort as, the standard quicksort is basically what is called a randomized quicksort. any other variety of quicksort actually should not even be discussed. Because in the interest of worst case analysis, why would you even run an algorithm where can be defeated very easily by giving you an input that is that ordered this way or that way. But moment I talk about randomized quicksort, then you have defeated that adversary. Neither the adversary has any control, nor you have any control. And every time basically I pick a pivot, yes, there is a probability of picking a bad pivot that is very small. So finally again, the kind of analysis, and you can think about quicksort also in the same framework, that the sequence of pivots could be thought of as a random permutation. Okay? Right? So I am going to basically pick the pivots exactly according to the random permutation. If the first element is 10, I will pick element 10. If the second element is 200, I will pick the element 200 and use it to partition. So that's the way I can run quicksort. And if you run the quicksort that way, then any of those pathological cases will not apply. Right? And that's the only way that you should be using or learning quicksort. The other one is, it was actually initially, the version defined by, the person who invented quicksort, Tony Hoare. But at that point in the 60s, there was no notion of these randomized algorithms. So he just defined quicksort in a way which was very simple, that you pick the first element, but he never said that you should always pick the first element. Or another way to think about it is that before you start running quicksort, you do a random permutation. Then no one has any control, right? My adversary gives me an increasing or decreasing order. What I do is I just shuffle the input. Gone. So again, it's back to the same case. Right? So I'm trying to draw your attention between what I just described for closest pair and quicksort. They are actually of very similar nature. So quicksort also, the analysis of a randomized quicksort is nothing but the expected running time of quicksort is averaging over all sequences of pivoting. So that's the parallel. So for the closest pair, I have set it up that it's the average over all possible permutations of adding those points. Here also it's very similar, and it's not even an accident actually. They are both. Quicksort can also be thought of as a randomized incremental construction where you're adding the next pivot, refining the partitioning, adding the next pivot, refining the partition, and you go on. Right? And so the nature of analysis is very similar. Okay? So if this is clear, then I basically try now to analyze this closest pair algorithm. I'm not going to get into quicksort right now, but I will analyze the closest pair. Right? So let me try to analyze the closest pair. So just recall this algorithm that I'm adding the points in a random order and maintaining some kind of data structure which I have not described here. So I have to now maintain a data structure, okay, such that this, I want to maintain a data structure such that this step can be done easily. So when we add the next point, this point, when we add the point pj plus 1, okay, we can check all the distances in this naive brute force manner. But what we really need to find out is that so we want to design a data structure, a efficient data structure to compute okay. So we'll replace this by some kind of data structure trick now. We are not going to take the new point and find out all the distances. It may not be necessary. All we need to know is that what is dj plus 1. How can we compute dj plus 1 from So, this is where basically all the efficiency will come from.
Data structure will not let us to recalculate the distance when a new point is added.
Well, sometimes we may have to recalculate. So, if you look at this scenario, depends on what is the ordering. So, for a certain kind of ordering, we will have to recalculate. But now I am going to exploit the randomization part, that how often do we have to recalculate? That is what we will come down to. So, first let us discuss some data structure for this. Okay. So, now I want to basically discuss a data structure. To maintain or recalculate, I would say. So, we want to basically keep track of this number, right? Because if it does not change, there is no, we do not have to do any work. Okay? And for that, let us do the following. So, inductively, we have computed delta j. So, let us go to delta j plus 1. Okay. So, let me do the following for this is for basically the set Pj, right, the first j points, and this Pj is basically defined by that random permutation. The first, so let me put in bracket, the first j random points. So, let me define a grid. Okay. We have not discussed this algorithm, right, in the previous, have we or have we not? Is this algorithm actually discussed previously by any other lectures? Okay, good. I do not want to repeat that actually too much. So, I define a grid on the plane. No, has this algorithm been discussed? No. That divide and conquer algorithm was discussed. Okay. And we have these points. Okay. So, it is an infinite grid basically on the plane, right, and this grid basically will have, I have to define the dimensions of the grid. Okay. So, the grid will be, you might have guessed by now, it will be a delta j by delta j grid. So, these red points basically are this Pj, and this is an infinite grid on the plane. It is an imaginary grid. We are not going to actually keep it explicitly anywhere. Let us say that there is it is centered in, it is somewhere the origin is given. Maybe this is the origin. So, the grid is basically defined with respect to this origin, and these points in Pj will fall into one of the cells of this grid. Right? Most of the cells, of course, will be empty because it is an infinite grid and there are only j points. Okay? Most cells are going to be empty. Now comes the next point. Okay? So, Pj plus 1 comes in. Okay? Now, Pj plus 1 can be in one of the cells. Okay? So, let us say this is Pj plus 1. So, we can easily compute the cell containing. How do we compute this? We know the coordinates of Pj plus 1, some xj plus 1, yj plus 1 using normalizing with respect to the grid size. So, we will know exactly which cell it falls into. You divide by that the grid size, right. So, what is the coordinate basically, which cell it is going to fall in. The cells are going to be numbered by some integer cells can be like mn kind of, right. So, I need to know, so cells can be, oh, maybe I should write it down. Okay. The grid cells can be indexed by, let's say, sk, skr integers. So, I can do some kind of numbering that this is, let us see if I, this is like, this is 0 0. So, this could be like 1 0, this could be like 2 0, this could be like 1 1, sorry what is this, 2 1, etc. So, every grid basically has a number associated with it. That is the way I can identify a particular grid. So, there are infinite grids, so there are infinite numbers, but we are not going to store the infinite number of grid cells. We will only store the ones that will have some information, that is, that actually contain some points. And there can be at most j grid cells that can contain points, because they are j points. The empty grids will not even store. So, in some data structure, we will only keep track of the non-empty cells, right. So, let me point out that the data structure will only store the non-empty cells, and that is at most j. So, everything is finite, we are not dealing with the infinite thing, it is just a hypothetical grid that we have placed. So, now this point comes in and it falls into some cell. Now, from the information about the remaining cells and also about this cell, can we quickly determine whether or not this point can change the closest pair? So, I have chosen the grid cells to be delta j by delta j, right. So, right now the picture that you are seeing, okay, can this point actually change the closest pair? Just from the example that I have seen creating. So, the green point has come in, can it change the closest pair distance? The closest pair distance at this point is delta j, and the grid cells are of size delta j. So, information that we have is that the cells that contain red points are stored in the data structure. Okay. So, when can it change that or potentially change that distance? So, first of all, if there was a red point inside the same cell, right, there could have been a red point here. If there was a red point inside here, then that cell is stored, okay, and I can fetch that cell and check whether it is really close to that red point, and if so, then the distance is going to change. I need not look at any other point, right. So, I know which cell it belongs to. The cell is stored in the data structure, okay. I will just fetch that cell. The cell has an address. The address is given by that pair of integers sk. So, does sk contain a red point? If it does not contain a red point, it contains a red point, we should compute that distance and check. If it does not contain a red point, what do we assume? What can we conclude? Can we conclude that it cannot change? No. It can still change, right. For instance, here if you look across, basically now the, oh God, so you may have to basically look across the neighboring cells. Because there could be a point in the neighboring cell which is very close to the boundary and it could be less than delta. Essentially, is there a point that is potentially closer than delta? You rightly said, if I draw a radius delta j disk around Pj, and let's use green. Oh no, let's use green. So I basically draw a disk like this of radius delta j. Only points within this region will be closer, right? Now, of course, I don't know whether there are points inside that disk, but what I know is that whatever cells fall within that overlap with the disk, potentially if there is a point, red point in there, that could change it, right? But if those disks are complete, if those cells are empty, the neighboring cells are empty, then there is no chance that it could change it, and that's the test. Got it? Okay. So how much time do I need to follow this? Constant, yes, depending on the data structure. So constant means what we do have to do. So data structure basically is, so what I'll do is I'll just define the data structure and stop, and then we'll take a break and continue after that. So the data structure should support finding non-empty right. So given a cell, I should be able to find the non-empty neighboring cells. We are only storing the non-empty cells. Empty cells are never stored. Okay. So how quickly can you find the non-empty neighboring cells, and how many neighboring cells are there? So I first compute this one. This is the first thing that we do, okay, that we actually compute the neighboring cell, the cell that contains the new point, the green point, and then we need to fetch the cells, non-empty cells around it. So how are you going to store those cells and fetch those cells, and how many cells are there, possible cells are there? How many possible cells are there? How many cells can this disk intersect? Yeah, just about these, maximum of this A1 plus 1 cell, that where the green cell falls. So 9 cells basically, right? 3 by 3. So the 9 cells basically is like some constant, okay? So I fetch those cells, and how do I fetch the cells? I basically use these indices. So I need to store those cells in some way, like it's like a dictionary data structure essentially. I need, the address is basically S comma K. So I need to find out if those neighboring cells are present at all or not. I know the address of the neighboring cells. It's a dictionary lookup. I find out whether it is there or not. Now the dictionary lookup can be implemented as what? Now tell me. Any kind of binary search tree, you can store those cells, okay? Or you can do it in constant time if you were to use some clever hashing. So especially if you use, I would say, if you know what is universal hashing, then you can do it in constant time. Okay. So it depends on the data structure. It also depends somewhat on the model. Okay. That is a little subtle, but I will say, just leave it at this, that can be done in order log n time using BSTs, or even in order 1 time using universal hashing. So it's a very powerful method of hashing, again, which is randomized, and it works for any kind of input. It is not those, will have conflicts and things like that. So even in the conservative case, we can say that it takes log n time. So, in log n time, we will know whether or not this point is going to change my closest pair, right. So, if it changes the closest, if it does not change, nothing is required. What do? I just put the point in the data structure. I use the cell containing the data structure will be added to the existing set of cells. That is the easy part, right? Mm-hmm.
What is the, let's say, if I suppose I have drawn an entire grid
Mm-hmm.
and I have added some point, but each time why random numbers is required? I can take an arbitrary point and put and see where it lies and look at the neighboring where the changes have been taking place. What is the need to generate a random number each time when somebody is?
We will see. We are not finished the analysis. The analysis is still there. We will have another discussion. It will take another 15 minutes for me to go through it, take you through it. We will see that. That's the next thing. First, I am basically freezing all my data structures, okay, and basically what is doing. Finally, at some point the randomization is going to be exploited. Right now, there is no use of randomization anymore. Till now, okay. So, observation essentially is that. Maybe I should go to the next page. So, the observation in order log n time, we can verify if delta j plus 1 is equal to delta j or delta j plus 1 is not equal to delta j. So, this is a good case. No change is required. So, the new point is simply stored. Now, stored means also that data structure, the dictionary data structure, it takes log n time. So, we will take log n time to store it, right, update the data structure. Stored in the data structure. Log n time if you use BSTs, order 1 time if you use hashing. That done. This is the unfortunate bad case. Okay. This is, I think, you basically, if I were to draw this thing, you are going to shed some tears. Okay. So, what do? So, now you are back to basically recomputing everything. The whole grid has to be recomputed, right? So, you are really going to shed tears here. Okay. So, recompute the entire grid with delta j plus 1 and store cells. How much time will this take? Well, we are not doing it for all the endpoints. We are only doing it for the j plus points that we have till now, right? So, time order j log j actually, but I will say that is less than order j log n. All right. Now you see the stark difference between these two cases. The good news, the good case is that log n time. If every step was log n time, for the n steps you are n log n. You are done. Very good. You have an n log n algorithm. But disaster strikes if the other thing happens.